Hey, good afternoon. Let's get started with our lecture for today. So hope everybody had an opportunity to upload their lab for the first lab that was due on Monday. So today we're going to have our second lab. So I'm going to follow the same process. You're going to have some time to work on a problem. You're going to discuss it. And you will have until the end of the day to submit the answer for that. Today we're going to transition to a new topic. And this is a continuation of what we started discussing in terms of product design, process design, and schedule design. Today we're going to talk about flow and activity relationships. So, and how that connects with the design of facilities. So this is material that is covered in chapter 3 of your textbook, flow systems, activity relationship, and space requirements. And the idea is that you get an understanding about the different type of flow that you will encounter inside a facility. And also, how do you use that information to plan for the design of a department or a design of a manufacturing cell. So those are the ideas that we are going to study, or the topics that we are going to study in this lecture. So as always, I start my lecture with the objectives for this class. So, the material that we are going to cover today is connected to the majority of them. And the agenda for today is in this slide. So we're going to talk about flow systems, material flow system, and then departmental planning, layout types based on material flow systems. And we have another topic that is lecture part 2 for this topic, and that will be covered on next week. But for today, we'll be touching on those 5 major points, the first 5. So as I mentioned already, we want to have a good understanding of the interactions between flow systems, flow activity relationship, and space requirements as they relate to facilities planning. So let's talk about flow systems. So flow system is the movement of goods, materials, energy, information, and or people. So it could be any of these different, you can say, goods or different types of information, materials, people. So it's not just constrained to products. That's what we are trying to say. So a flow process might be described in terms of the subject of flow, the resources that bring about the flow, and the communication that coordinate the resources. And I don't know what's going on with the animation, but I apologize for that. So the subject is the item to be processed. So again, it could be goods, materials, energy, information, people. People in the sense, like, for example, if you're dealing with a healthcare system or an airport, that's the product in that sense. So you want to bring a service to that person. The resources that bring about flow are the processing and transporting facilities required to accomplish the required flow. And the communications that coordinate the resources include the procedures that facilitate the management of the flow process. So again, we have the subject, we have the resources, and we have the communications that coordinate the resources. So flow systems for discrete parts processes can be categorized according to the stages of the supply, manufacture, and distribution cycles. There are three categories: are materials management systems, material flow system, and physical distribution systems. And those are illustrated in this figure. So you see the correlation between them. So we have at the top, we have the vendor. And at the bottom, we have the customer. So the vendor is the supplier, is the entity that is going to provide you with the materials, the information that you need to build that product. Materials management system is going to take that information, it's going to take that material, and it's going to find a way to bring it to the manufacturing side. Inside the manufacturing side, we have the material flow. So you're going to be moving those materials. That movement is related to the process that you need to follow in order to get the final product. And then after the product is completed, you have the physical distribution system, that is what's taking the finalized product to the customer. And that's how you end this process. So three categories, we're gonna talk about each one of them individually. The materials management, the material flow, and physical distribution system may be combined into one overall flow system. Such an overall flow process is referred to as the logistics system. And we talk about logistics a lot now with all these major companies like Amazon and so on. So there's three areas, three categories. We're going to talk about each one of them now. So let's start with the material management system. The material management system has the flow of materials into the manufacturing facility, again, from the supplier to the manufacturing floor. The subjects of material management systems are materials, parts, and supplies that are purchased by a firm and required for the production of its product. And we talk about making sure that you have a reliable supplier, making sure that supplier is going to deliver when you need the materials, because if you don't have that, then you cannot manufacture your product. So first step, the materials management system. The resources of the material management systems include the production control and purchasing functions, the vendors, the transportation and material handling equipment required to move the materials, parts, and supplies, like when you get the deliveries from the truck, all that transportation from there to the site, the receiving, storage, and accounting functions. So very important, right? You have to keep record of what's coming in, what's coming out the facility. The communications within materials management systems include production forecast. Let me move this in here. The inventory records and the stock requisitions, among others. So there has a communication aspect. There's exists a communication aspect also, as we mentioned already, within the material management systems. So we have information about the forecast, what we are expecting in terms of sales. We're planning our production schedule based on that. So if we expect to sell, let's say over the Christmas season, we're going to sell more items. We are planning up for that forecasted demand, and we plan for purchasing those supplies based on that forecast. We have to keep the inventory records up to date, meaning knowing how much material we have already in store or in the facility, and the stock requisitions, meaning that we put those orders at the time that we need to, so we can get those materials on time. The overall flow for materials management system is presented here. Again, you use the forecast, production forecast, to plan for the amount of supplies that you need. That goes to the production control. They say, okay, based on those forecasts, these are the number of supplies of each type that you need for production. You make those stock requisitions, and the purchasing department is the one in charge making those orders. Those purchase orders go to the vendors. Once the vendors are getting those orders, you go through the transportation, from the vendors to the receiving department. So now you get those parts into, or the supplies into your facility. You have the accounting department involved to pay the vendors. And then once you have those materials in the receiving department, you use your material handling to move the materials, and then the cycle goes back to the beginning. So now that we have a understanding of the material management system, we can transition to the next level, which is the material flow system. And this is inside the facility. So we get the supplies into the facility. Now we're dealing with what's going on inside the facility. So the material flow system, the flow of materials, parts, and supplies within the facility. The subjects of material flow systems are, again, materials, parts, and supplies used in manufacturing products and components within its facility. The resources of the material flow systems include the production control and quality control departments. Now we are looking at the departments inside the facility. The manufacturing, assembly, and storage departments. The material handling equipment required to move the materials, parts, and supplies, and the warehouse. Okay, so if you think about designing a facility, now we are thinking about those departments: production control, quality control, manufacturing, assembly, storage departments, material handling equipment, and the warehouse. All those things have to be part of that facility. Communication includes production schedules, work orders, releases, tickets, Kanbans, barcodes, route sheets, assembly charts, and warehouse records. If you don't know what Kanbans are, we're going to talk about that as part of our lecture on manufacturing systems. But for now, these are cards that are used to plan for the production inside the facility. The material flow system. Again, we have a flow chart here. We start with the production schedule. So this is what we're going to produce in the next week, in the next month. We send that to the production control, and the production control is going to release the work orders according to the schedule. We move those tickets inside the facility according to the route that each product needs to follow. The material handling is in charge of, again, distributing or moving those parts according to the flow required for the completion of the product. And then the manufacturing departments are the ones that are going to be working with the part or the supplies in order to make it the final product. We get to the assembly department, and once the product is completed, we send them to the warehouse. Once we update the warehouse records, we go back to the beginning and the process is repeated. So we have information. Maybe I forgot to mention, here's the key for this diagram. So we have the flow subject. These are the parts that are moving through the system. You can see that it's sequential. And we have some information in terms of communication from this point till you get to the warehouse. The last piece is the physical distribution system. So once we have the product ready, what will happen? We have the physical distribution system. The physical distribution system, look at the flow of product from a manufacturing facility. The subject of material flow systems are the finished goods. Okay, so that's again, once you have completed the process, you have a final product, you are dealing with the finished goods produced by the firm. The resources of the physical distribution system include the customer, the sales and accounting departments and warehouses, the material handling and transportation equipment required to move the finished product, the distributors of the finished product, and that's it. The communication includes sales orders, packing lists, shipping reports, shipping releases, Kanbans, and also the bills of landing, meaning that you have completed the process of delivering the product. So the flow chart for this part, you start with the customer. This could be a store or this could be a supermarket if you're thinking about HEB. They say, okay, I need this. That goes through the sales department. Sales departments send that to the warehouse. Warehouse look at the availability. If it is available, we move the supplies. We send an information in terms of the invoice for the customer. We're gonna complete that order based on what you requested. Once the payment is completed, we transport that product to the distributors for transportation to the customer. Okay, so 3 major components. We start with the process at the beginning where we get the supplies that we need to process. Then we move to the manufacturing component. How do we process those supplies? Then we get the finalized product. How do we distribute that? Which is the physical distribution system. Okay, so going back here, we went through these 3 pieces of the process: material management system, material flow system, and physical distribution system, from vendor to the customer. Any questions? I know I'm presenting a lot of information. We're gonna do some math in a few minutes, but you need to understand what we're dealing with in terms of the facility, how the facility is interacting with these other pieces, and the flow that is happening inside the facility is gonna help us plan for the layout. So let's talk about material flow system. We will focus on material flow systems with emphasis on flow patterns and structures as viewed from the perspective of flow within workstations, within departments, and between departments. So in terms of our focus for planning the design of a facility, we need to understand the flow between or within the workstations inside the departments of the facility, and between those departments in the facility. When I mention flow within workstations, we are going to look at motion studies and ergonomic considerations. We don't go in detail in this for this piece because there's a class that focuses on that. If you are in IE, we have the methods, engineering, and ergonomics. And part of that class focuses on the ergonomics in terms of designing the workstation for the workers inside the facility. So flow within workstations, flow within departments. This discussion will focus on flow within product, process, and product family departments. So there's a difference between them, and we're going to talk about that now. For a flow within a product department, the flow of work follows the product. Okay, so what that means is the everything that we are designing for a product flow will be focusing on that specific product, and everything will revolve up around the product. The flow of work follows the product flow, and here we have some flow within product departments, examples. So for instance, here we have two stations that product is going to move from this station to this station. That's called end-to-end. Here we have another layout in which we have the tables facing each other. And what's going to happen here is the product will go to this table and then move forward. That's called back-to-back. Front to front, here we have the employee in the middle. Here we have two employees on the sides of the tables. Here we have the employee in the middle. So the flow will go here in this direction, and that will be also manufacturing both sides. Circular, the name, you have this arrangement of tables in a circular flow. So the product will go from one table to the other and to the other until it's completed. And finally, we have this odd angle, which is very similar to the A. The only difference is that you have a different shape, we can say that way. And typically this will happen because you have a fixed equipment or a column in that area. So you have to accommodate that with changing the angle of the flow. For different ways of showing the flow within product departments. So in this part, basically what you have is you start the product and you finish the product in that same department. Flow within the process department, similar or identical machines are grouped in the same department. So now instead of starting the product and finishing the product in that same department, you're taking the product into different departments in order to complete the process. So what will happen is you have a group of machines in the same department, and if you have to go and do some drilling, you have like 20 drills in one department, and you take the product there, you do the drilling, and then you move it to a different department to complete the process. So flow in the process department, we have similar or identical machines are grouped in the same department. A minimal amount of flow should occur between workstations within departments. Flow patterns are dictated by the orientation of the workstations to the aisles, and the determination of the preferred workstation aisle arrangement pattern is dependent on the interactions among workstation areas, the available space, and the size of the materials to be handled. So again, different configurations for flow within process department. You have the parallel, so you have those machines located next to each other. We have the perpendicular, right? So you have the machines perpendicular to the aisles, and then you have the diagonal. So you have that diagonal shape with the aisle. Essentially, there's no difference between them. The only difference is how you are, the angle that you're using to locate those machines, and that will depend on how much space you have and how many machines you want to locate inside that department. Also, aisles are very important. So if you're constrained with a single aisle, you might choose one configuration. If you have two aisles, you might choose another configuration, and so on. And then the last one, which is the flow between departments, is criterion often used to evaluate overall flow between or within a facility. The location of the pickup and delivery stations for each department is important. So why is that important? Well, depending on, let's say this is your final department for a process, you want to make sure that you're close to the docks for shipping. So knowing where those are located and knowing the flow will help you align your process. So when you finish the process, you can take the product easily to the shipping area. So that's why we call this, we need to take into account the location of the pickup and delivery stations for each department. So if your flow is, in this example, your flow is starting in the same place where the flow is ending. So that will be the case, for example, if you have to take the process, this component within this department, and then bring it back to the previous department. So you started in department 1, you go through department 2, and then you bring the part back to department 1 for additional processing. So knowing the beginning and the end of that process can help you design the flow. You want to start and you want to end in the same point, but that's not always the case. In addition to that, you might design the flow according to the location of the machines, right? So if you have parallel machines in this way, or maybe not, maybe you have a flow that looks like this, depending on the machines that you are using. But both of this have the entrance, the input and the output in the same location. So that's A. B is right here. They have the input and output on adjacent sides. So you have the input here, and then the output next to it. Same thing here. In C, we have them on the same side. The only difference is that it's not the same. You have entering at the top and then leaving at the bottom. And then this one is on opposite side. So you start in one place and you leave through the other. So all those patterns are relevant because they influence the design of your department and also the design of the overall facility. You want to make sure that when you start designing the flow within the department, you take into account where the flow needs to start and when the flow needs to end. So you can plan the inside of the flow within the department. So effective flow planning is a hierarchical planning process. And here we have the hierarchy, flow planning hierarchy. So we start with the effective flow within workstations, effective flow within departments, and then the effective flow between the departments. The following principles have been observed to frequently result in effective flow. We want to maximize the maximization of directed flow path, meaning that you have the direction very well established. So if you move from left to right, you keep that flow from left to right. There's no way for you to go from one direction to the other. So we want to maximize that. The minimization of the total flow, meaning that you can get as many parts within the department without having to keep them inside that department for a long period. And the minimization of the cost of flow, meaning that you are not using, well, you're trying to minimize the amount of material handling that you need to get the parts from point A to point B. So those are principles that has been observed to frequently result in effective flow. Okay, so Based on that, let's talk now about departmental planning. And in this part of the lecture, we are going to talk about an algorithm. And then we're going to solve a problem based on that algorithm. So departmental planning. So in this case, we are trying to figure out, for example, if we have different type of products, how many machines of a certain type we need inside the department, and so on. So planning departments can involve production, support, administrative, and service areas. Production planning departments are collections of workstations to be grouped together during the facilities layout process. Okay, so production planning, you are doing some type of activity in your product with a machine, an assembly, or something else. Depending on product volume variety, production planning departments can be classified as product fixed materials, location, product family, or process planning departments. So 3 different types: products with fixed material location, product family, and process planning. And what's the difference between them? We can observe the difference here in figure number 9. It will depend on the volume and variety of your production process. So for example, if you have a very low variety of products and a very low volume of products, let's say you are manufacturing a boat or a cruise, right? So that's very low variety, very low volume. For those cases, you want to have a fixed location layout, right? So you bring everything to the product and you build the product on that location. So fixed materials location planning department. That's the type of department that you want to build. On the other side, let's say you have a low variety, but with a high volume. Those cases, you have a product department or a product layout. We're going to show some examples soon. Same thing, if you have very high variety, low volume, you want to proceed with a process planning department. And if you have a medium variety and a medium product volume, you look at the product family planning department. So product family planning department could be, let's say you're manufacturing cell phones. They share most of the technology will be the same, but there will be different in certain things, like you have different Samsung models or iPhone models. So you can classify that as a product family, and you can take that through a product family planning department or product family department. And then you will just keep some of the stations that are not necessary for that product. Overall, you follow the same flow, but if you need to skip some of them or you need to add some of those steps, depending on the product, you can do that with a product family department. So in this table, showing a procedure guide for combining workstations in planning departments. So let's start with the left side of the table. If the product is standardized and has large stable demand, then the type of planning department should be a production line or product department. And the method for combining workstation into planning departments should be combine all workstations required to produce the product. So for example, when I was working for Johnson & Johnson, we have a Tylenol product, right? That has very standardized Tylenol. Everybody know about the product with very high volume, right? So for that volume in terms of demand. So for that type of product, we can have a line and we can run as many batches that we need to get the volume that is needed by the customer. And if we need, I don't know, 3,000 pallets, we can run those 3,000 pallets through that line. So we have a production line for a product department. If the product is significantly large, upward to move, and has a low sporadic demand, then as I mentioned, fixed material location, product department, you combine all workstations required to produce the product with the area required for staging the product. So boat, an airplane, you get the idea, right? It's something that you're not necessarily building them every day. You need a long period of time for completing them, and demand is low. There's some demand for it, but it's low. So a fixed material location product department. If the product is capable of being grouped into families of similar parts that may be produced by a group of workstations, then we follow with the product family or product department. We combine all workstations required to produce the family of products. So as I mentioned, the cell phones, that's an example. Computers like Dell computers, you will have a product family department. Some computers will have the chip, some computers will have this screen, but at the end is the same family of products. And if it is none of the above, we have a process department in which we combine identical workstations into initial planning departments and attempt to combine similar initial planning departments without obscuring important interrelationship within departments. So if none of this apply, then you are trying to put as many workstations together so you can design a process or a flow for taking those products through the facility. Okay, so departmental planning, product family departments. Product family departments aggregate medium volume variety parts into families based on similar manufacturing operations or design attributes. Machines required to manufacture the part family are grouped together to form a cell, thus the label cellular manufacturing. The direct clustering algorithm methodology is a simple procedure that clearly illustrates the important features of the cell clustering problem. The direct clustering algorithm is based on a machine part matrix in which 1 indicates that the part requires processing by the indicated machine, and a 0 or a blank means or indicates the machine is not used for the particular part. So now I'm introducing this way of, or this algorithm that can help us plan for the number of machines that we will need within a cell and manufacturing cell for medium volume variety parts trying to accommodate into families. So the DCA methodology consists of the following steps. These are the steps of the algorithm. Step 1, we're going to have a matrix. Okay, so the idea is that you have a matrix like this. And you will have information about the machines, and the products, and a 1 is going to tell you, okay, part 1 needs to be processed by machine 1. If there's a 0 or an empty space, that means that that part is not going to be processed by machine 2. There's a 1 here, then that means part 1 has to be processed by machine 1 and machine 3. And we will have a matrix like that one, and that's what that's representing. For each part, it tells us which machines needs to be which machine needs to be used to process each type of part. So, see. So this is the idea. You have the machines numbers and you have the part numbers and you have that information inside the matrix. So this algorithm is gonna allow us to plan for cells, manufacturing cells. Basically, we want to build these cells and we can tell the department, okay, we build a cell that can be used to process part types 1 and 2. And then we build another cell that can be used to produce parts 3 and 4. Okay, so we want to make the minimum number of cells possible. Well, not necessarily. We want to group the products on cells so we can minimize the number of machines that we need to buy or we need to have inside the department. Okay, so we're going to start with ordering the rows and columns, and we're going to sum the ones in each column and in each row of the machine part matrix. Then we're going to order the rows top to bottom in descending order of the number of ones in the rows, and order the columns left to right in ascending order of the number of one in each. Where ties exist, we're going to break the ties in descending numerical sequence. Step number 2, we're going to sort the columns beginning with the first row of the matrix, and then shift to the left of the matrix, all columns having a 1 in the first row. Continue the process row by row until no further opportunity exists for shifting columns. And in step number 3, we're going to do the same thing, but with the rows. We're going to sort the rows column by column, beginning with the leftmost column. Shift rows upward when opportunities exist to form blocks of 1. Performing the column and row sortation is facilitated by using spreadsheets such as Microsoft Excel. So what that comment is trying to say is we're going to attempt to do this by hand, but if you can set it in Excel, it will be easier to visualize. And then after we have completed step 1 through 3, we want to form cells. We're going to look for opportunities to form cells such that all processing for each part occurs in a single cell. So let's look at an example. So we want to apply this direct clustering algorithm method to group 5 machines. And the entries in the matrix indicate the machine part combination that is required. So again, this matrix is telling us that machine part 1 needs to be processed by machine 1 and machine 3. Part 2 needs to be processed only by machine 1. Part 3 by machines 2, 4, and 5. Part 4 by 1 and 3. Part 5 by just 2. And part 6 by 4 and 5. So we want to, using this information, we want to know how many cells we can build. So we are allocating products to 1 cell. So if I end up with 2 cells, I want to tell in this cell, I'm going to manufacture parts 1, 3, and 5. In this other cell, I'm going to manufacture parts 2 and 4. That's the information that I want, because using that information, I can design my department and build the number of cells that are needed to manufacture these parts. Okay, so let's try to apply the algorithm. I'm going to look for the steps here so I can refer to them as we move forward. So step 1, we want to sum the ones in each column and in each row of the machine part matrix. If you look at this matrix, I already have those summations. So for each row, I have the totals. So for the first row, that's 1 plus 1 is 2. For the second row is 1. For the third row is 3. Fourth row 2, 5, 1, and then 6 is 2. And I do the same thing for each column. The total of ones for the first column is 3. The total of ones for the second column is 2, 2, 2, and 2. Okay, so that's the first step, or the first part of the first step. Now, I want to order the rows top to bottom in descending order of the number of ones in the rows, and order the columns left to right in ascending order of the number of ones in each. So after applying step 1 of the direct clustering algorithm, the rows are ranked in descending order of the number of ones. So you see that now. You see the totals. I have ordered those from the highest number in the rows to the smallest number in the rows. So now row 3 is at the top, row 6 is second, row 4 is third, and so on. You see here we have a tie. So for these 2, we have a tie, and for these 3, we have a tie. So how do we break the ties? We put first the part number with the highest number. So these 3 are 2. So I'm putting 6 first, 4 second, and 1 third. They have the same number. So I'm arranging them based on the part number. So 6 first, 4 second, 1 third. Same thing for the last 2. So 5 third, and then 2 second. Now, in terms of the columns, you see that instead of going from largest to smaller, we're going from left to right, from smaller to larger number. So now the machine numbers are 5, 4, 3, 2, and 1. For the first 4, we have a tie, right? We have 2, 2, and 2, and we break the tie in the same way. So we put 5 first, 4, 3, and 2, and then 1 is the last one because it's the one with the highest number. Okay, so that process that I just discussed is step 1. So you start by adding the number of ones for each column and each row. Once you have the totals, you want to reorder the rows from the biggest value to the smaller value, and you want to reorder the columns from the smallest value to the larger value, from left to right. And this is the matrix that you have so far after completing that process. Questions? Okay. So ties are broken in descending numerical sequence. The row order sequence of part numbers is 3, 6, 4, 1, 5, and 2. Likewise, the columns are arranged in ascending order of number of ones, with ties broken in descending numerical order. The resulting column order sequence of the machine numbers is 5, 4, 3, 2, and 1. 5, 4, 3, 2, and 1. Okay. So that's step 1. Step 2 involves sorting the columns to move toward the left, all columns having a 1 in the first row, which represents part 3. Since the columns for machine 5 and 4 are already located to the left of the matrix, only the column for machine 2 can be shifted. Okay, so what we are saying is, let me use another color. For step 2, I'm going to start looking at each row. So this is my first row. Okay. And I'm going to look at the ones in that row. And I want to shift to the left. If you have a 1, you want to move all the ones to the left. So you see, we start with 5, it already has a 1, so I don't have to move that one. Go to 4, it already has a 1, I don't have to move that one. 3, there's no 1 there, but 2 has a 1. So I want to move 2 to this position. Okay? So that's what you're seeing here. You have 5, 4, 2, 3, and 1. The reason why is you want to push the ones towards the left. And you're going to do that for each row. So for example, here I move 2 to this position. So now I have 5, 4, 2, and 3, and 1. After I'm done with this row, I need to go check on the next one. Here, I mean, once I look at 5 and I say 5 has a 1 and is located there, that is fixed. I don't move 5 anymore. Since I move 4 is not moved, so 4 is fixed. Once I move 2, 2 is going to be fixed. So the only 2 that are left are 3 and 1. So I go to the second row, I see that there's no 1s here. Maybe that will make more sense here. So let's assume that I already moved 2, right? So I go to the second row, I check for 3 and 1 because 5, 4, and 2 are fixed at this point. I already moved 2. So I check 3 and 1. I cannot move 1 because 1 has no 1s here. So I move to the next one. And what happens here is that both of them have 1s. So at that point, I know that these 2 are going to be fixed. I'm done with the shifting to the left. Okay, so I know this is the first time that you're seeing this, so we are going to practice. At some point, this is going to be automatic. Okay, but that's the idea. You start with the rows, go to the first row, you move all the ones to the left, you're done. You fix those that have 1s towards the left, those are fixed. Then you keep working with the last 2 in this case until you find a way to fix those as well. And we end up fixing those 2 here. Okay, so that's for step 2, involves sorting the columns to move toward the left, all columns having a 1 in the first row, which represents part 3. Since the column of machine 4, 5, and 4 are already located to the left of the matrix, the only column for machine 2 can be shifted. Okay, so step 3 consists of sorting the rows by moving upward rows having a 1 in the first column that they are not ready located as far as the top of the matrix as possible. Okay, so the idea now, once you have done the shifting to the left using the rows, now we are going to change the focus. I'm trying to change the color. It's not. Okay. So now instead of looking at the rows, I'm going to start looking at the columns. And I want to start moving up those columns that shows a 1. So if I look at this row 3, that has a 1 already, this one has a 1 already, and the rest of them have no 1s. So those 2 are fixed, 3 and 6 are fixed. Now I look at the second column, there's nothing there to be moved. So those are stay the same, 3 and 6. When I look at the third column, I find a 1 here in row 5. So that one has to be moved after 3 and 6. So that row is going to be moved up after 3 and 6. Okay, so row 5 is going to be moved up, and that's what you're going to see here. So now I have 5 after 3 and 6. If you look at 4 and 1, you look at this column, after you make that shift. 4 has a 1 and 1 has a 1, so we don't move them. And then when you go to the last column, the only one that has a 1 is that one, but those 3, 6, 5, 4, and 1 are already fixed, so there's nothing else that you can do. And at that point, I'm done with the algorithm, step 3. So we start with adding rows and columns. We sort them according to highest to lower, lower to higher, from left to right. And then I start looking at each row, if I can move columns to the left, and then I look at each row, and if I can put them above, move them upward, and then I'm done. So I have this. Now, using this information, I can see that I can group the machines in 2 cells. How do I know that? Because there's this group right here are not interacting with machine 3 and 1. They're only using machines 5, 4, and 2. So I can tell, parts 3, 6, and 5 are only produced by 5, 4, and 2, so I can group them in a cell. Okay, I can create a cell to produce those parts. And this group right here are only using machines 3 and 1, so I can have another cell which will be in charge of parts 4, 1, and 2. And that's the idea behind the algorithm, that we can find those clusters, we can separate the clusters, and we can plan for the number of cells that I can have inside a department. Okay, so I now know that I only need 2 cells, and I can separate the products based on those 2 cells. And that's what's illustrated here. That's not always the case. Okay, sometimes you will see there's conflict, that there's one machine that is needed by all the products, or is needed by some of the products in the first cell, and also for some of the products in the second cell. So how do we fix those problems? So I have an example here, that is trying to illustrate that point. So using the DCA method to determine alternative groupings of machines, I start with this information, and suppose that applying the direct clustering algorithm methodology results in the following order machine part matrix. So this is the result. So after applying the method, this is what the result is. So I now want to see if I can split this in 2 cells. Notice that because machine 2 is needed for parts 3 and 5, this is machine number 2, is needed by parts 3 and 5, a conflict exists. 2 cells can be formed, one consisting of machines 4 and 5, these 2, and one consisting of machines 1, 2, and 3. However, we're still pending with that second machine because it's also needed by part 3. So the machining required for part 3 of machine 2 needs to be resolved. So this is what I'm marking here with a star. So that's what's creating the conflict. So what do I do? As an alternative, I can go the other way around, and then the conflict will still exist. Instead of having the problem with part 3, I now have the problem with part 5. So solution number 1, if machines 2 and 3 can be located relatively close to one another in different cells, then part 5 could be processed by machines on the boundaries of the cells. So the idea is, well, one solution could be you have a cell here, you have a cell here, and then you are putting that machine in the middle. So you have one machine here, one machine here, and this will be how the conflict could be resolved. Another option is to duplicate machine 2 and place it in each cell. So what this is saying is, okay, we might need to buy another machine, and then we can place that machine, one of those machines in one cell and one of those machines in the other cell. So another option is to duplicate machine 2 and place it in each cell. Another option is to duplicate machine 3 and place it in each cell. So decisions will be made based on space, cost, and so on. Okay, so let's try this. I know I have talked a lot. It's been an hour now. So I want you to try to apply the direct clustering algorithm to this example, and that will be your lab number 2. So if you have a piece of paper, you can attempt to solve this using the direct clustering algorithm. For this problem, you will have, the solution will give you 2 separate cells without conflict if you do the algorithm correctly. So let's try it. Let's attempt this, and then I'll give you 5 minutes. And after that, we will discuss it, answer questions, and then you will submit this by tonight. Remember to work on your own and try as much as you can. That will tell you if you have doubts, if you have questions, then ask those questions, we'll clarify, and then you will understand better. Okay, so let's try to solve this. So we're gonna start with the summation for each column and each row. So here we have 3, 2, 1, 1, and 2. And we have 3, 2, 2, and 2. Okay, so we know the totals at this point. And the first step has, in addition to computing the totals, we have to do the sorting for rows and columns. So we're going to start with ordering the rows top to bottom in descending order. So order rows top to bottom in descending order. So if we do that, we will have, so this will be the part number. This would be 1, 5, 2, 4, and 3. And this would be 1, 2, 3, 4. And the matrix will look like this. So 1, 1, 1, 1, 1. So that's by ordering only the rows from top to bottom in descending order. So we end up with 3, 2, 2, 1, and 1. The next step is to order the column from left to right in ascending order. So order columns left to right in ascending order. Okay, so columns left to right in ascending order, we will have 4, 3, 2, and 1. And the rows will be the same. 1, 2, 1, 5, 2, 4, and 3. And the matrix will look like this. 1, 1, 1, 1, 1, 1. So that's the resulting matrix after the sorting. Totals here will be 2, 2, 2, and 3. Left to right, ascending orders from left to right. Remember that the ties are broke using the index of the, in this case, the machine number. So that's why 4 goes first, 3 goes next, and 2 goes next. So at this point, we have the matrix in the format that we need. So now we go to this next step, which is step 2, and we're going to look at each row, and we're going to move once towards the left. Okay, so we're going to start with the first row. We're looking at this row right here, and we see that for 4 we don't have to move because 4 already has a 1, but we have a 1 here and a 1 here, and 3 has no 1. So I need to move 2 to the left, and I need to move 1 to the left, and then 3 to the last position. So that's what I'm going to do. So row shifts to the left. I will have 4, 2, 1, and 3. And the rows are still the same, 1, 5, 2, 4, 3. So column 4 is the same. Now I'm moving to questions? Questions? No. So I'm moving 2 to the left, right? So 2 will be next to 4. This will be 1, 1. I'm also moving 1 to the left. So this will be 1, 1, 1, and then 3. So that will be the new matrix. If I go to the next row, since I already fixed 4, 2, and 1, because 4 was fixed from the beginning, has a 1 in the first row. Then I move 2 and I move 1, those becomes fixed. So 3 will be fixed by default because the other 3 are already moved. So I don't have to go deeper in this case. I have the columns already in their location. Now I move to the shifting of the rows. So I'm going to shift the ones towards the top. And I'm going to start per column. So I'm going to start with column 4, this column, and I'm going to check if there's any ones that needs to be moved up. The answer is yes. For that first column, I have a 1 here. So I need to move that row up. Okay, so that will make, so this is 4, 2, 1, and 3. Now I'm moving, 1 is fixed because I already have a 1 there, but 3 is going to move up. So 3 is going to be here. And then I go to the next column, 5 is gonna be fixed after that. So 5 has a 1 here. So 5 is fixed, nothing else happening here. Then I have 2. 2 is fixed, so the last column will be 4. Last row, I'm sorry, gonna be 4. So it's 1, 3, 5, 2, 4. And the matrix will looks like this: 1, 1, 1, 1, 1, 1, and then 1 and 1. So I'm sorry, I said that you were gonna have a clear separation. That's not gonna be the case in this problem. We're gonna have to look at so this is the final matrix. Maybe. 2 row should be a 1 here, right? Yes, correct. And that's what's creating the conflict. So if you try to split this into 2 cells, you'll see that you will always find a conflict. So if we split through here and here, this machine will have a conflict. Same thing, if you try to split it, it doesn't matter how you try to split that, you'll still find a conflict. So machine 1 is needed by both cells. So as I mentioned already, you have different ways of solving that problem. You can put 1 in between the 2 cells, or you can duplicate machine 1, and you can assign 1 machine to one of the cells and 1 machine to the other cell. So if in the exam or in the assignments you end up with something like this, I will expect you to elaborate on your plan. You identify that there are 2 cells, 1 machine is needed in both cells. So this is how you're gonna solve the problem. Easiest way would be to buy a second machine and assign that machine to one of the cells and the another machine to the other cell. Okay, and that will be correct. Okay, so just keep that in mind. Good. I think we have used all our time today, so we're gonna continue next week. Remember, Monday is Labor Day, so we don't meet on Monday. There's a holiday. We'll meet again on Wednesday. Okay, and I think you will have an assignment posted today, and that will be, or I don't remember if I posted already or not, but typically the assignments are due in a week. So check on Canvas and see what that assignment is due. And remember to submit your lab today. Any questions? Nope. So I'll see you next week.